My name is Sumit Purohit. I'm data scientist, and as mentioned, my research has always been around graph theory and applications of graph modeling. Started with way back when ontologies and semantic web were not cool. I was doing semantic web and ontologies, graph data modeling. Uh, Continued that with graph neural network, and nowadays language models and agents that with graph can be used to solve specific domain problem. So this presentation has been prepared keeping very high-level introduction of the topic in mind. But at the end of it, if you have any specific question, please feel free to reach out to me. Let's start with story of a hammer. So hammer was not invented. It was actually observed. And over the course of thousands of years, different civilizations identified different use cases, refined the design of hammer, also categorized the hammer into different classes for which kind of problem, which type of hammer is useful or not. And the interesting observation about this story is the initial part of the hammer, the refinement were not science-based. No one was looking at the material property of it, the length of the hammer, face, claw. These properties were not quantified, but it was more of an experience and art. So for the so many initial years, hammer was improved with a combination of experience and art. And what we have today is the culmination of that. Maybe we have a new hammer in the world today. We have seen the same story so many times, wheel, engine, even the algorithms. Initially, it starts with experience and art and intuition, and then we try to identify what are the patterns which are working, which are the patterns which are not working, and how do we make progress in a well formal way. So I start my talk with a bit of optimism and openness that this new hammer that we have in the world today, it's going through a transition period. So we are witnessing something really interesting and intriguing. And this is the end of my philosophical slide. What we have seen, the large language model and last presentation was a really good example. We got really great detail of it. Just to summarize that they are trained, these are AI systems which are trained on vast data. That's the main difference between earlier language models or even earlier AI models and these large language models. And they excel in natural language understanding, generation, and various natural language tasks. One key technical advancement that happened was transformer architecture. This was the architecture that made a large leap of jump, and that make these kind of models much better than all other AI models because they had better understanding of long range dependencies. Earlier, RNN, CNN, they were really good in understanding maybe the next sequence or maybe previous sequence and next sequence and have a limited understanding of what that either the line or the paragraph was trying to say. What transformer model brought was much more understanding and the capability of learning much larger context. So that at that level, it appeared like a human level intelligence, and that's made them really interesting. So they are really good in lots of applications: text generation, summarization, correlation, and explanation. And there is a history of this. This is just one part of the timeline. Now it has evolved quite a lot. But at the same time, they are not good in many of the tasks. So here is me asking ChatGPT, who is Sumit Purohit? And it says it's Sumit Purohit, me, is a versatile professional, known for his work as a filmmaker and data scientist. As a filmmaker, I have done so many great things in some of these Indian stories, web series, and these are real web series, and that's right. On the scientific front, I'm a senior data scientist at PNNL, and I do graph analytics, I do knowledge graphs, ontologies, large-scale model. So in summary, ChatGPT think that Sumit Purohit's career span significant contribution to both fields of media and scientific research. The interesting thing is the first paragraph and second paragraph independently are true. There is a media person in India with exact same name, and these are his credentials. He's very famous. But the problem is with smoothness and the confidence, language model summarizes that and say, well, Sumit Purohit is the same person. And that is not only just wrong, but it's very dangerous. What if instead of Sumit Purohit, it was part of some very critical decision-making process, and it started doing that kind of a correlation where it's not true. It's fundamentally not true. So that's the aspect of language model, which is really these models, out-of-box models are not good at. I always say, and maybe this audience is a right audience for that example, I think of language model as my high school friend who will always give you an answer, irrespective of he or she knows that answer or not. And he will give you with so much confidence and smoothness. So retrieval-augmented generation is an emerging design pattern. I'm not saying this is a new technology. It's a design pattern that reuses existing technologies. It's a design pattern of LLM-based development that has shown improved accuracy and addresses key challenges: hallucination, provenance, and knowledge update. Hallucination, the last slide was an example of hallucination, where it started saying something and didn't stop where it should have and made that leap and said something which was entirely not true. Provenance. Out-of-box language models, at least at some point of a time, had no access to the individual source where that fact has come from. It has learned something, but it cannot go back in its memory and say, I learned this from this book, this web page, this tutorial, or this conversation, or this experimental study. And knowledge update. We always see ChatGPT, Claude, or all these other models are frequently updated. The update cycle has improved a lot, but still we are stuck on one timeline of those language models. And if something has happened after that timeline, language model doesn't know that. But we as a user and we as a human expert, we are up to date, much recent than these language models deadlines are. Okay, so key idea of retrieval augmented generation is generation is from language model, but retrieval is something that comes from external sources. So the key idea is that we have an external, updated, and domain-specific knowledge outside of language models training data that we can use to generate context and ask question before language model. The key difference is the naive approach is user ask a question to language model, get an answer, update his or her own understanding, ask the next question, and keep that cycle. But in the RAG approach, before we ask language model, we first ask something that we have high trust on, that is domain specific, that understand the context of the question, the concept of that question. We ask question to that sources, and I'm not saying single sources, multiple sources, and build a common understanding, and then ask language model the question. So the key differentiation between these two approaches is that we have something external to language models that are high confidence. And as I said, it need not to be one source. It can be multiple sources. We can frequently update those sources. We can restrict those sources to the kind of questions, kind of problem we are interested in. And that's the key difference between a naive language model use and RAG language model use. And that step is called retrieval because you have a lookup or you have some similarity before generation happens. So let's go deep dive into a RAG approach. RAG approach has primarily 3 phases. Again, the way things are changing, the way concepts and theory are changing, it's not true. Maybe in future, there may be a bit more refinement of these steps, but as high level, there are 3 steps. The first step is embedding generation, which is called pre-retrieval. Whatever knowledge you have, which is specific to your problem, you generate embeddings of those sources. So looking at, hopefully this, yes. So you have your data sources that goes through text, metadata, and chunking process. And using some sort of embedding models, we generate embeddings. And simply embeddings are vectors of numbers that represent something which is said in the natural language text. And we store that data into some vector stores. Vector stores, just like any other databases, are databases, but they are specialized in storing long vectors of numbers, and they are really fast in operations related to vectors, such as cosine similarity. That's the key contribution of RAG approach, and that's the key contribution of vector steps too. The second step is retrieval. Before we ask any question to language model, we first ask some form of question to our vector store. And the third step is LLM query augmentation or pre-retrieval. So we got a question. This is the original question you intended to ask a language model. That question again goes through the same embedding model. We have some query embedding. Remember, this is an offline process. You have already done that, store it somewhere. Now, on the inference time, you have your question. It goes through the same process. You get a query embedding and try to find similar content based on your retrieval. So if my question, for example, is about Georgia, or if my question is about Turkey, just saying that word doesn't give me entire context. But if my rest of the question is about building a recipe, then maybe I'm not talking about geographic location Turkey. I'm talking about the Turkey, which is the recipe of it. So that overall aspect, before and after aspect of the query and the key terms that construct the context. And based on that, I get some retrieval documents. Maybe if I had no such aspect, language model will start talking about geographic location, but I have already queried or retrieved some recipes, and now these recipes are going to LLM and saying, hey, I'm looking for something about Turkey. Here are the relevant documents. Now give me the answer. So the key thing is we should use language models for common sense. We should not use language model for facts checking. Common sense is really good because it can correlate things. It can provide you a summarized and very short answers. So common sense aspect of language model is still true, but the retrieval aspect should come from these language models, these vector stores. Okay, so I just want to highlight these 3 key components of RAG. One is embedding model. Embedding models take something and generate numbers. I'm keeping it oversimplified, but at the end of it, these are some numbers that represent some meaning in the real world. Second is vector stores. These are databases that are efficient to do semantic similarity and storage for long vectors. And the LLM, which we know out-of-box language models either are trained for general purpose applications or even fine-tuned for specific applications. So let's go a bit deep into first part of it, which is embedding models. So embedding models are kind of a portal between discrete and continuous word. You have a continuous space, a lot of things said, either the words or images or part of the component. And then discrete things are when you categorize something into a smaller dimension. So here is an example. What embedding model does, they are algorithms that translate high dimensional data into lower dimensional data. What I mean by high dimensional data is if there is a word, there are many dimensions of that word. What is its language? What is its connotation? What is its meaning? Is it positive, negative? There are so many ways a word can be described. So if I have to describe a single word, these are multiple aspects, aka dimension of that even word. Instead, we specify them a long string of numbers. Now, The advantage of this approach is it enables downstream applications that are trying to use those numbers to perform something called semantic similarity between entities. So things which are similar in natural language will be similar in this lower dimensional space. Here is an example. A sad boy is walking is much closer to a little boy is walking rather than a dog is walking past a field. So both have common words, but their meaning and their semantics are quite different. And if there is a way of saying, if the question is about, look how sad my cat is, instead of looking a little boy is running, these are two semantically distinct concepts. Whereas, look at my little cat, that's slightly similar concept if you think of it. And this is the capability that we get from embedding models. Taking something which is in high dimension, converting it into low dimensional, so that if things are similar in high dimension, they will still be similar in low dimension. We take these numbers, store in vector databases, and now it becomes really efficient to just do a cosine similarity. And things which are similar in cosine space will be similar in high dimension too. Here is a real world example. So what I'm showing here is Wikidata. Wikidata, just like Wikipedia, it's a collection of concepts. It's multilingual concept. Almost every famous entity, country, people, location, event, they have Wikipedia page, and they are translated into Wikidata pages too. This shows the clustering of those concepts in low dimensional space. This is the cluster that talks about music. This is the cluster that talks about sports. Here is a cluster that talks about military positions. This is some of the political concepts. And here, some of the Ukrainian election concepts. The idea here is it reduces the chances of conflict of concepts. If I'm, for example, talking about, again, Georgia, if I'm talking about Georgia or Turkey, is it from some of the recipe which is here, or it's some of the political scenario from here? That gives us really a grounding in the domain. So if I'm building a portal or an application for recipes, I will go to recipe pages. And if I'm building something on the political and election specific problem, then I will go to different embedding clusters. So here are some of the examples. There are many embedding models. This list might not be fully updated, but we started with Word2Vec, and now last I have used is text embedding 3. The things that's changing with progression of these embedding models are the size of that embedding. Given a word, how many number or what's the size of that vector that number is getting created? That's the only difference between it. As the number increases, it increases the granularity of differentiation between very minute differences in the concept. So larger the embedding size is generally good. Completing the aspect of RAG about the storage. Where do we store these numbers? You can store it in text file. You can store it in CSV files. Nothing stops, because at the end of it, these are just numbers. But vector storage are kind of a vault for everything with a meaning. So these are specialized database that offer efficient storage, indexing, and search operation. It enables precise similarity search using approximate nearest neighbor. So this is a bit technical detail of that. What they are trying to do is, given a data point in real world, they try to identify what are its nearest neighbor in the low dimensional space. And the hypothesis is those neighbors are semantically related to the questions or the data points that we have. These are really ideal for AI ML applications, facilitating tasks like clustering, classification, and anomaly detection. If you already have something in that space, it's much easy to identify, as I showed in the last slide too. It's really easy to identify what is the common cluster of it, what are the anomalies, why this point is different than rest of it. So that kind of applications vector databases make it really, really simple. Some of these vector databases, which are open source and you can use it in any of your applications, Chroma, Pinecone, and Face. I think this is Facebook application. I primarily use Chroma because it's really easy to integrate, and existing language model frameworks such as LangChain, AutoGen, they are well integrated within this ecosystem. Let's now look at the second part of the RAG, which is prompt and template. I think these two concepts you will hear multiple times because it's really crucial. How do we form our question to language model? Prompt is an instance of some instructions given to a language model. And if you have used ChatGPT, you can create your personas. If you have used AI Incubator, we can also create our personas. That personas are kind of a meta level instructions, and then you start asking questions. So prompt is an instance of a complete question that goes to language models. Then template is a parameterization of that prompt. A prompt, if you know the pattern in a prompt is it asks about some keyword, is it adds some related context, and that's the parameter. You make them as a variable and then build a web application where user is providing these two things, or you are extracting from vector databases and keep reusing the same template for multiple prompts. So prompt and templates are also used in RAG approach too. What they instruct, they identify about the query processing and how to retrieve context from vector database. It can give language model which vector database to call, how to extract, how many similar things to extract, that kind of instructions we can add. Prompts can be used for a few short examples too. Language model have shown really good understanding. If you provide them few examples, they quickly understand what the intentions of end users are, and they try to generate answers replicating that same format. It's kind of a, okay, someone is asking me my answer in given format, let's generate that format. And just a bit more technical detail, how do they generate that? They actually generate multiple answers. Some of them are not exact in the format user have asked. So there is a sampling process that happens behind the scene. So they generate 100 answers for your questions and then pick one which is closest to the format that you have requested. So these are just the technical detail of that. One really interesting aspect of template structure is how do we instruct these language models? And there have been multiple reasoning loops or multiple reasoning patterns that has been observed. So if you ask language model to internally think it through before answers is given to user, it has shown much more refined and improved accuracy. And not all language models are equipped to do that. Before GPT-3, there was no reasoning, but gradually a lot more reasoning has been added to it. So when you ask your question, don't say, do that and give me the answer. Add some instructions to validate the answer internally before it is shared with end user. So that's the design pattern or the meta design approach called REACT. Reasoning traces, where you ask someone, here is the action, here should be your observation. There is another steps of validating that. And if there is something wrong with the overall approach, go back. Don't just give me a partial answer. Go back. So a language model can internally go back multiple times. And now with the advent of agentic approaches, we can build agents which are doing exactly those same steps and forcing language model to regenerate the answer and forcing language models to validate every answer in different criteria before answer is shared with end user. Okay, so in one of my slides, I showed that the key difference is you have a set of external sources. Now, how we use those set of external sources are unbounded. And that's why multiple classes of RAGs have been developed. Again, this is the part of experience and art, which we have been going through right now. There are standard RAG, which says, have a question, do semantic similarity, ask LLM. And then there are graph RAG. Before we have embeddings, we also create something called knowledge graph. Knowledge graphs have connection across documents. If you have a set of, say, 10,000 documents, you can ingest them into a vector database by embedding models. But which entities in which paragraph are connected to document A and document 999? Are these two documents related or not? That level of meta connection and meta concept alignment can be done through language models, knowledge graphs. So knowledge graph is another aspect of RAG, which has been developed. Agentic RAG, every application is given to a specific agents. Streaming RAG, where some of the agents are well equipped and added with some of the streaming applications like Kafka. So it's a front end for any language model application, and self-reflection RAG. So these are different varieties of RAG, but the key aspect is you don't ask your question directly to a language model. You have something in between which you have much more control and which much more confidence in. So I will go a bit deep into one of my own research work called Graph8. Graph8 is an advanced graph-assisted query and reasoning system. It's a generative AI capability. It's a RAG application. What we have done is this is an agentic graph RAG approach where we have a knowledge graph in addition to vector databases that we can use. And the novel contribution of Graph8 is that it brings and it integrates semantic web technologies such as ontologies, knowledge graph, into Gen AI technologies. So the entire process is guided by an ontology from the ingestion, generation, question answering. There is an aspect of ontology. What does a person means? What is the definition of a person? What is the definition of a city? That kind of a concept. It also decoupled embedding models from embedding models and LLM. All the examples we generally see are language-based embedding models, where there is input is a word, multilingual word, and output is some number. What about the input is not a word, but a FASTA sequence? So then AAA, BBB, CCC, they are not semantically similar to AAA, BBC, because there is a different layer of functional correlation in those FASTA sequences. And Graph8 decoupled that process, and I have an example of that too. At the end of it, we are trying to expedite the whole development of digital assistant. If we have a problem where we have grounded multiple high confidence domain specific data, how can we build a graph RAG application and perform question answering? This is the overall architecture of Graph8. I'll not go more detail into it, but at the end of it, if you have any questions, please feel free to ask me that. The key aspect is there are two phases. The first phase is when we have domain specific data that goes through an embedding steps, and at the end of it, we store vector databases, and if there are any graph databases. And domain expert provides some templates which says, remember, I'm getting this kind of a data, that's how you should interpret it. And at the end of it, what we get is a vector database of those documents and a fused knowledge graph where all the entities are connected. And then there is a second phase of this, where user is interested in asking the questions against those bunch of documents which are stored and the knowledge graph which is created. Every question is translated through. Now, before I go a bit more into details, these icons, these are all LLMs. They may be the same LLM or they may be fine-tuned and specialized LLM. Another way of thinking them is these are the agents that are specialized doing some task. So when user asks a question, this agent translates that natural language question into multiple variations of that question, because what you are asking may be asked in a different ways. How about we ask 10 different questions to our RAG approach rather than your own question? The key is we should maintain the intent of user query. We get multiple variations. All those variations goes through our semantic similarity approach, where we have vector database cosine similarity. At the same time, all those questions goes through another agents that create a subgraph template for every question. Every question can be translated into a subgraph template, which, if subgraph matching occurs, can provide you the results to your question. I'm skipping how the subgraph matching aspect is happening, but please feel free to ask me that question. So at the end of it, suppose you have your graph stored into Neo4j, assuming that we know what Neo4j is. It's a graph database that provides you a query language called Cypher, and you can ask a graph pattern and do the query reasoning. So we get graph matched subgraph, and we also get matched paragraphs, and this agents combine that. Here comes the correlation, reasoning, and common sense part. This is an agent that got some matched subgraph, some matched paragraph, and it distill everything and create a summary and return it back to the end user. Again, I'll provide one more example in the domain that hopefully this audience is used to of all. So we worked on something called Graph VAE this was a Gen AI and PPI initiative project where we are trying to predict functions of microbial using this RAG approach. So predicting, I'm not the expert in this room to talk about this topic, but predicting functions from amino acid sequence is challenging due to complex sequence structure functions. So either we can do very expensive multiple experiments, or we can do some sort of a computationally expensive and time-consuming protein sequence alignment. These are generally two approaches when we have a sequence which we are not sure of what its functions are, and we are trying to predict functions. These are two different approaches we can use. What RAGE VAE work leverage is it leverages Gen AI techniques to integrate and aggregate experimental metadata and gene fitness data from 84 microbial species across thousands of experiments. We have access to multiple fitness data for multiple genes and multiple mediums, and we are trying to identify fitness value of some of those genes in the medium where we don't have experimental data. This is again going back to the RAG approach. We are trying to build a digital assistant that can help domain experts to identify, at least set up their own experiments for the gene and for the medium where they have no experiment for. This flow should look a bit similar because this is a RAG approach. What we have are protein sequences. Remember, I talked about decoupling natural language-based embedding models with something like this. So now we have a protein sequences. They goes through multiple one-hot encoding sequences and some sort of a normalization. And at the end of it, we also use another open source protein similarity model, which is based on variational autoencoder. And at the end of it, what we get is some similarity that we store in our vector database. Remember, we are interested in some numbers that says number of this sequence and number of some other sequence. If those numbers are similar, that means there is some grounding that these two sequences are similar. So these sequences goes through another contextual retrieval, and rest of the pipeline that I showed in the overall architecture, that's where we use we have trained a vector quantized variational autoencoder model, because embedding models need not to be a language specific embedding model. Anything that's maintains similarity of your given domain, that's good enough for a RAG approach. What we are trying to do here is we have three different types of data sources. The first one is these FASTA sequences that goes through our embedding models. We have all those embeddings and they are stored in vector databases. The second source for us is we have fitness values, fitness experimental data. From that, we create a knowledge graph of chemical, mediums, protein, and functions. This is heterogeneous knowledge graph, and we store it in a graph database. In our case, it's a Neo4j graph. And then we have a set of publications. Those publications where domain experts have much more confidence that these publications does talk about the kind of a problem I'm working with. So that again goes through language-based embedding models, and again are stored in PDF, ChromaDB, some sort of a vector database. So first one is not language model-based embedding model, but the third one is natural language-based embedding models. It goes through uh, the overall extraction process, and then user asks, this is the offline process, and then user asks a question, what is the function of BWI76 in glucose medium? I'm sure many of you knows better than this, a better answer of this question. But so if this is the question, first it extract the overall pipeline, extract the protein, then it goes through this embedding process and identify what other proteins are similar to that proteins. So only one protein is mentioned in the question. Now it gets maybe 5 more proteins which are similar to this. Then it goes through graph similarity and try to find what is the connection of that 5 additional and 1 original protein within the graph database. What are their predicted functions? What are their already known fitness values? And it combined that context. And then it goes through many publications and say, hey, I believe this paper has already talked about this kind of experimental setup, and here are the suggestions of setting up the problem, here are the possible solutions, and here are the recommendations from those papers. So combining everything, that goes to language model. So thinking from the language model point of view, it gets this question, and instruction says, hey, don't just hallucinate and start giving me answer. Restrict yourself in these additional knowledge that I'm providing you. Your answer should be between that given protein and the additional proteins. It should be within those publications, and it should be within the graph structures that I'm preparing it for. And that, again, using the common sense of language model, it provides us a response. Looking at an example of it, so if this question was asked to language model, it identify, so I ask this question and I say, provide me a summary in 50 words and also provide a list of conclusions. So whatever the highlighted things are, they are not part of language models training data. That's not out of box ChatGPT or Claude. That's coming from either my vector database from semantic similarity of publications or proteins, or it's coming from this kind of a knowledge graph, which is a protein conditions functional annotation knowledge graph. Internally, Graph8 goes through and perform a graph walk, construct some paragraphs, and send it to language model. So it's really good in summarizing it in the format we ask for. So here is the function, organism, medium, fitness, and implication. And that kind of a question is hard to get from out-of-box ChatGPT, because it have no access to these databases. And we don't want it to train it on those databases either. So in conclusion, retrieval-augmented generation is a design pattern. It still uses the same technology stack, language model, embedding model, programming environment, but it's a design pattern, how we use these technologies to efficiently and quickly develop some capabilities for a specific problem. It enhances language models application by providing guardrails. And guardrails by means it restricts language model to just start saying you something and start technically doing hallucination, because it is restricted and it asks to not say anything which is not mentioned in the additional context which it is provided. And also the ground truth domain for many applications where we want to provide provenance and facts where that information is coming from, and that's very critical in many domains. That's also very critical novel contribution of RAG approach, because it has access to individual paragraph, individual node in the graph, individual document where it's getting that context from. And the embedding models and vector storage are really integral part to RAG approach. As I said, it's a design pattern. So embedding models are used in multiple ways. We continue to use them in RAG, but we use it in a slightly different sequence of things such that language model is much more informed. And that's why it's retrieval augmented generation. With that, I conclude, and this work is done on multiple projects. I would like to, there was a slide, I think I missed it or it didn't translate it, but work from Jochen, Pat McKee, and Joseph, and on Rage, VAE, Winston, Rob, and Sam Donald. We are working on multiple projects developing these capabilities. With that, if you have any questions, let me know. That's a second example. If someone is more interested in multiple applications, I can do that. But that's it. Thank you.
Yeah, thanks, Sumit. We'll start with questions. Looks like we've got a couple already.
Hi, thanks for your wonderful presentation. So how good is a VQ VAE model compared to traditional homology or orthology based predictions?
So from the Gen AI and RAG point of view, these are black box model. If they are similar, that's the evaluation step we can do. I am probably not the expert of those similarity models. That's where the domain experts comes in picture. They have metrics of validating how good their similarities are. But this is a topic that we have explored and we continue to explore. We have not used in current pipeline.
Yeah, just as a follow-up to my previous question. So if we want to predict protein and its function from a species that was not part of the training, like you said, 84 microbial species were used for training, right?
Yeah.
Then how would it perform in case of that? Like just a complete new species, and would it be able to generate the sequence similarity or something like that based on the training, or how would it work?
So that's where different knobs on your overall pipeline you can have. You can either ask language models and the overall system to not predict anything which is not seen. But at the same time, if language model have seen some either the protein or entirely different structure of something, then you can ask it. I'm open to that kind of suggestions, but that has to have a specific agents that validate those sequences. Because in the current pipeline, we were focusing on don't predict anything which is not seen. But that's a valid question. Are we open to those kind of suggestions or not? Before we are open to those suggestions, we have to develop some validation agents that says, here are the new suggestions. Let's validate it either externally or with human expert in the loop, and then follow with the same pipeline.
Thank you.
I'm very interested in like the embedding aspect of like how you Hello? Hello. Okay. How do you determine the embedding machine for different types of information, especially to capture the similarities that could be seen with like words or sentences, but going to like graphs and images or videos?
So that's a question the team takes, because we know what kind of a similarity we are looking for. If we are looking for similarity, so we know our domain. If the problem is from natural language domain, we should go for natural language based embedding models, because every embedding model is trained on its own domain. If you take a language model, a natural language embedding models, and send protein sequences, it won't work. And it's not supposed to work because they are trained on that domain. Okay. Because they are trained on that domain, picking up the right embedding model is really crucial. And another crucial aspect is using the same embedding model in the overall pipeline. Offline process, you cannot use one embedding model, and in the query time, you start using different embedding models. Because what changes? Their semantic learning parameters changes, their vector sequence changes, and that's why the cosine similarity is not exactly same if you just change. Give you an example. I was using text embedding 2. I had my whole application built using text embedding 2. And then through AI incubator, I could only use text embedding 3. The things which were similar in text embedding 2 space were not similar in embedding 3 spaces. So I have to retrain that. So consistency of embedding model is really crucial in the RAG approach.
Thank you.
Thank you for the wonderful presentation. So I wanted to ask some few questions. So you mentioned different type of work patterns, where you mentioned the standard work, the agentic work, and stuff like that. So I wanted to ask that how do that different from workflow, in the sense that is standard work and is the typical example of a workflow
Yeah.
as compared to like agentic work? Because I know this is a kind of very expensive to make, and especially if you're working on a kind of a small project. So when do you decide that, okay, I'm going to develop like an agent based tools instead of just like a workflow, something like
Yeah.
that?
So agentic patterns are some sort of a workflow. The difference is right now we are in that experiments and art phase of the overall technical progression. Gradually, we'll identify which workflow pattern works and which workflow patterns are appropriate for what kind of a problem applications. So workflow is very generic term. Doing a sequence of things in parallel or conditional, that's a workflow. So RAG approaches our workflow where you have your user question and you have some specific data sources. How do you use it? So at the end of it, I totally agree. It's one of the workflow, but which workflows work for what kind of a problem? That's the key advantage. So we have identified RAG is a design pattern, and adding language knowledge graphs to it is useful. Adding some sort of a reasoning to it is useful. So these patterns, these ideas are getting solidified as we build more and more use cases of it.
Yeah. Also, a follow-up question on that.
Yeah.
So when you mentioned about the functional prediction of proteins using the RAG agent-based tools, right? I wanted to ask about the fact that we're trying to solve the problem of hallucination. And I know like many scientists now, they are interested in generation of new proteins that are maybe more thermostable.
Generation of, sorry?
Like generation of like proteins, like
Mm.
generation of like sequence of proteins that, maybe they are very important to industry, but they're not like microbial based, right? And I wanted to ask, like, what is the role of like RAG based in trying to design a new protein or something like that? It's not just about functional predictions of like what we have seen before,
Yeah.
but like a kind of a generation of a real protein that would kind of solve the problem of that hallucination, and that something that like the experimentalist or people in a specific domain could follow up and like get something important from that.
Yeah. My intuition on that is agentic RAG approach would work better in those kind of application. Assume that you have an external model, AlphaGo 2 or AlphaGo 5 or something, which can predict or recommend some of those structures or some of those unseen protein. We can build those agents that interacts with those external tools and bring in the information that's provided by those external tools into the overall workflow. So agentic tools, which are agentic RAG, is one design pattern or meta design pattern which I think would work better on that.
Okay.
Regarding this graph Rage VAE application, during lunchtime, we have another presentation from our team member, Winston, and you can ask some of these embedding related and protein similarity questions to him too. He's presenting similar work.
Yeah. Any more questions in the room? Anything online?
So someone online is asking about whether there is a tutorial that you might recommend that would either help replicate or let someone train a RAG model to predict protein function, or if there are other resources you might recommend.
If I recommend something today, tomorrow, that won't be updated. So keep yourself updated. I can share some of the work we have done, like Rage VAE work, and also some of standard tutorial from on OpenAI and LangGraph's workflow systems. Those are really good. At the end of it, I can share some of the links of posters and papers that we have presented. But as I said, don't stick with one tutorial, because whatever is true today may not be accurate tomorrow.